Okay. By the way, I put for you a video, which is a recording of my lecture from last year. Okay, so it is the same slide for this lecture, only I didn't change the slide because I worked very hard on them. But the numbers are different. Okay, so you will see that they are lecture 19 to 21. Don't worry about it because we moved the orders of the lecture. Okay, but they are exactly the same slides if you want to listen to the video. Okay, so we said we're going to define today the glucogenic and the ketogenic. This is going to be the topic of Thursday, which is how we make amino acid and what are the essential and the non-essential amino acids. Okay, so the metabolism of amino acid, first thing we need to remove the amino group. Once the amino group is removed, we can metabolize the carbon skeleton into one of these 7 products. Okay? Sometimes it's just easy because if you just remove the amino group, you will get pyruvate for which amino acid? Alanine. Okay? But for phenylalanine, for instance, to become fumarate, it is a multiple reactions. It's not so simple. Okay? But you should know that the metabolism of the 20 amino acids at the end will give me one of those 7 products. Are you required to know these 7 products? Yes. It's very easy to know them. Okay, we have the acetyl-CoA, acetyl-CoA, which are, if they are given, it means that your amino acid is ketogenic. Why ketogenic? We said because these 2 are precursor for ketone. Okay, we can use them to make lipids, we can use them to make energy, but we cannot use them to make glucose. Great. What about those 5? What is common about those 5?
Glucogenic.
4 of them are in the Krebs cycle. Fumarate, oxaloacetate, alpha-ketoglutarate, and succinyl-CoA are intermediate of the Krebs cycle, right? And we have pyruvate, which is the end product of glycolysis. What is common among all of them? I can use them all to make glucose. And this is why if an amino acid is broken down to one of these, it will be classified as glucogenic. So I can use it to make glucose, energy, and also lipid, because you know that we can go from glucose to lipid. Okay, so this is the center of today's lecture, how to classify amino acids as glucogenic, ketogenic, and what are these amino acids broken to. We know, we have seen before, like simple example, alanine, you remove the amino group, you get pyruvate. Which amino acid will be degraded into oxaloacetate? Aspartate. You remove the amino group, you get oxaloacetate. Similarly here, which amino group you can remove? Amino acid, you can remove the amino group to get alpha-ketoglutarate? Glutamate. Those 3 pairs, you should be very familiar with them the way you know your name, okay? You should know the enzymes, you should know the cofactors also. Okay, so these are the 7 products. Again, you see them here. So the intermediate of the Krebs cycle, the pyruvate. These are the products that make amino acid glucogenic. And these are the 2 that make amino acids ketogenic. Okay, but I want you to look at tryptophan, for instance. Tryptophan can be broken down to give me pyruvate and acetoacetate. So how do I classify tryptophan? Both. Okay, because its metabolism can give me a molecule precursor for glucose, and also a molecule which is a precursor for ketone body. So it will be classified as both. Can you find another example for a molecule? Phenylalanine. Okay. Where is phenylalanine? It's here. It can give me fumarate, but it can also give me acetoacetate. So phenylalanine is both gluco and ketogenic. Okay? Tyrosine is another example. Okay? We will come back to them later, but this is the classification depending on what is the end product of their catabolism. Okay? So gluco, keto, or both. The glucogenic, we have defined them before we started the lecture, that these are the one that will give me pyruvate or one of the these 4 intermediate of the Krebs cycles. Are you required to know them? Yes. What are these 4 intermediates of the Krebs cycle? Okay, so you need, no, not pyruvate. Pyruvate is not in the Krebs cycle. Okay, these are the 4 intermediate of the Krebs cycle. So all these molecules can be converted to glucose, and if an amino acid is broken down to one of these, then this is a glucogenic amino acid. What about ketogenic? They will give me acetoacetate or one of its precursors. So these can be used to make fatty acid and ketone, but not glucose. So we classify them as ketogenic. And it turns out that we only have 2 amino acids which are exclusively ketogenic, and these are leucine and lysine. They made life easy for you. You can easily remember that the 2L, leucine, lysine, they are K, ketogenic. So KL, it's very easy to remember. Okay? What about the amino acids which are both gluco and ketogenic? So these are phenylalanine and tyrosine. I told you before, we need to convert phenylalanine to tyrosine by hydroxylation. We will see the reaction later. And then tyrosine can be broken down to fumarate and acetoacetate. So phenylalanine and tyrosine are both gluco and ketogenic. Isoleucine will produce acetyl-CoA and succinyl-CoA. So again, it is both keto and glucogenic. Tryptophan will give me pyruvate and acetoacetyl-CoA. So again, it is both keto and glucogenic. This is the classification in your book. Very easy to remember. This is the KL story. What about this? If you want to find a clue to remember which amino acid are both gluco and ketogenic, what would you remember? What is common among most of them here? Yes, so tyrosine, phenylalanine, and tryptophan are the aromatic amino acids. Okay, so these aromatic amino acids are both gluco and ketogenic. Isoleucine yes, cousin of leucine, leucine. So it is both keto and glucogenic. Okay, what about the rest? How would you remember them? Exclusion. By exclusion. Just remember that leucine, lysine is exclusively ketogenic. The aromatic plus isoleucine are both. Then the remainder, how many? What will be the rest? How many we have here? 4, 6. So the 14 remaining amino acids will be classified as glucogenic or exclusively glucogenic. Clear? يعني exclusively. Ask me in the exam who doesn't know the meaning of exclusively. Exclusive, yeah, it comes on the TV, right? So everybody should know what is exclusive. Okay, let's do this simple learning check. Who want to answer this question? Yeah, because you heard them say. Okay, so knowing the trick that I taught you, how would you answer this question? Yes, please.
We would exclude lysine because it is ketogenic.
Okay.
Tryptophan, isoleucine, phenylalanine. 2 of them are aromatics and isoleucine.
So these are the both keto and gluco. So by exclusion, okay. Another way to find the correct answer, we have learned many times about our ALT friend, which will become our friend now, ALT. Alanine, if you take out the amino group, you get pyruvate. There is no other molecule coming out, only pyruvate. And pyruvate is the gluconeogenic molecule or precursor, so it can be used to be converted to glucose. Therefore, alanine must be the only glucogenic molecule. صح? You agree? You don't agree? What about you, Baaz? Do you agree? Why alanine is exclusively glucogenic, Baaz? You don't know? You want to help him? Well, I know. What about you? You want to help him? Sit down. Pyruvate is ketogenic. Let's try to concentrate, okay? Thank you. So, when needed, the carbon skeleton of amino acid is going to be used to produce energy. How it is going to produce energy? By forming one of the intermediate of the Krebs cycle or one of the intermediate of glycolysis. Okay. What the products that I'm receiving or I'm producing will depend on the number of carbon that I have in an amino acid. So if I have a 3-carbon amino acid and I remove the amino group, I'm going to have a 3-carbon product. For instance, here, alanine is 3 carbon. I remove the amino product and get pyruvate. Okay? So the number of carbon, so 3-carbon skeleton in this amino acid will give rise to a 3-carbon skeleton molecule. We will come back to these many times, but aspartate is actually derived from asparagine by amidation, but asparagine can be broken to aspartate, and aspartate, again, the famous enzyme AST, will transaminate, yes, aspartate into oxaloacetate. Here, the 5 carbons molecule, so they can give me alpha-ketoglutarate. So how do I go from the amino acid to the intermediate of the Krebs cycle or glycolysis? It depends on the amino acids. Some amino acids, they are converted to these intermediate just by removing the amino group. Okay, as I've said before we start the lecture. So I gave you the example of these two. Also this one, how can I go from glutamate to alpha-ketoglutarate? What is the enzyme?
AST.
Which enzyme will take me from glutamate to alpha-ketoglutarate?
Reversible AST and ALT.
Okay, so it is the reverse of AST only? Only those 2 enzymes? Excellent. So glutamate dehydrogenase can give me alpha-ketoglutarate from glutamate, and we will come back to this. But what else besides AST and ALT? Let's see if you understood my lecture, 8 and 9. How many transaminases we have? 2. Only 2? Now we studied 2. How 20? We have lots of transaminases. It's a family of enzymes. AST and ALT are only 2 of them, but there are a family of transaminases. Okay? So all because we said in lecture 8 that the amino acid, I think all of them except 1 or 2 can undergo transamination, then donate their amino group to who?
Alpha-ketoglutarate.
To alpha-ketoglutarate. So the transamination not only of alanine and pyruvate, the transamination of most of the other amino acid will give rise to glutamate. This is one way. The other way, like your friend correctly said, glutamate dehydrogenase, okay, will produce alpha-ketoglutarate, which is the oxidative deamination of glutamate. Okay, so how we go from asparagine to aspartate? By deamination. Again, removal of the amino group, but this time it is not transamination, it is not the glutamate dehydrogenase. Here we have something called asparaginase. Similarly, for glutamine, we have glutaminase. Okay, but all of these share the same thing, and we go from the amino acid to the intermediate of the Krebs cycle or glycolysis by simple removal of the amino group, whether it is transamination or oxidative deamination or deamination by special enzyme like asparaginase and glutaminase. Clear? Okay, so this is what we have explained. So asparagine is converted to aspartate by the enzyme asparaginase. So here I'm not transaminating, I'm just taking out the amino group as a free ammonia or ammonium ion. As you can see here, so this is the amino group. What is the amino group in asparagine?
COH2, the first carbon.
How many amino groups we have in asparagine? We have 2. Okay, asparagine and glutamine have amino group in the R. Okay, so the R group side chain has an amino group, so they have two amino groups. So if you remove the first amino group, you still get an amino acid, which is aspartate. Okay? You just go from one amino acid to another by removal of the amino group in the R. Once you remove the second amino group, which is attached to the alpha carbon, this is where you get the oxaloacetate, which is the intermediate in the Krebs cycle. Okay? So we just say here that asparagine, to go to oxaloacetate, we need the enzyme asparaginase first to give you aspartate, then AST to give you oxaloacetate. Clear? Okay, so I'm not going to go through that again. You should know it by heart now. This is the ALT reaction. So alanine to give you pyruvate, it will donate to its amino group. You can see it here. To alpha ketoglutarate, so alanine will become pyruvate. This is a 3-carbon, this is a 3-carbon molecule. Alpha ketoglutarate will gain the amino group, will become glutamate. It's not always that simple, okay? Some amino acid to give me an intermediate of the Krebs cycle, they need to undergo many steps. Only Bashir will be required to remember this reaction, and I will give you a special exam paper, okay, by name to you, where you will be tested on this reaction. Let us find out what is the missing here between the arrow from other reference, okay? And I will test you on them. But for you, you are not required to know these steps, just to give you an example that it's not always one-step reaction to make the intermediate of the Krebs cycle. Many enzymes and many steps are required before you can produce a precursor of glucose. Okay. What about this? So we have some different funny scenarios in amino acids. We have these two couple which are interconverted. So glycine can give me serine, which is funny. On the way of degrading glycine to pyruvate, I have to convert it first to serine, which is a bigger molecule. Serine is bigger because glycine is the smallest amino acid. What is the R in glycine? H. Okay, so glycine is the smallest amino acid. To change it into serine, I have to donate to it a hydroxymethyl group. Who's going to give me this hydroxymethyl group? Yes, so this molecule, which is a nice name that all of you, including Bashir, need to know, and 5 and 10 methylene tetrahydrofolate. Okay? So it has tetrahydrofolate in it, but it has a methylene group, a methyl group. Okay? It will donate the methyl group to glycine to become serine. We'll come back to this many times. You will see it 4 more times in the lectures. But this is just, in this case, to illustrate that to go from glycine to an intermediate in the metabolism, here this is pyruvate, which can give me glucose. I have to convert the glycine first to serine, and then serine will give me pyruvate. Clear?
Yes.
Okay. Similarly, it's not always easy to go from phenylalanine to a glucogenic precursor or a ketogenic precursor. I have to undergo many steps. So phenylalanine, although it is one step to go from phenylalanine to tyrosine, but tyrosine, will have to undergo many chemical reactions before it can give me those two. Okay? طيب. Phenylalanine is changed to tyrosine by hydroxylation. Okay, we will come back again to this reaction many times. We need to add OH group to phenylalanine to make it tyrosine. So the enzyme is hydroxylase, and the cofactor is now not tetrahydrofolate. What is the cofactor? It's the first time you see this cofactor. It's tetrahydrobiopterin or TH. Not FP. Yes, it's a THP, tetrahydrobiopterin. Okay, so we will doesn't choose. When you break down tyrosine, you'll get those two molecules after a series of complicated reactions. Okay, we'll come back to this. Now let us do a simple exercise to keep you alert. I want someone from the back.
Yeah.
Riyadh? Can you answer this question, Riyadh, please? Yeah, sorry. This is very easy, Riyadh. Excellent. Alanine is glucogenic.
ابدا ما حدا عنده
تساعدوا ما بدي تساعدوا ليش تساعدوا؟
ما شاء الله عليك يعني.
Is what? Okay, yeah, عم بيتحذر. أنا ما بيتحذر. I don't want guessing. I want someone to answer. Ahmad, yes.
A is glucogenic, B is ketogenic, C, D, E are glucopatogenic.
Okay, C is what? Both. Because we've just seen in the previous slide that phenylalanine is will give me fumarate and acetoacetate. What about aspartate? It is glucogenic. Okay, it will give me oxaloacetate. We have said this many times. And glutamate will give me alpha-ketoglutarate, therefore it is glucogenic. Okay? If you get stuck in the test and you don't know what to answer, just remember the KL, okay? Then the aromatic are both, and by exclusion, the rest will be glucogenic. Okay? The last part for this lecture is this beautiful pathway here that all of you, including Bashir, need to know step by step. We will come back to this slide 3 times. So you have lecture 9, 10, or 11. Okay? So don't worry if you don't get it from the first time. This is a very important slide. Okay? We are using it to describe how we degrade amino acids. So to degrade methionine, first I need to change it into cysteine. And then cysteine will be broken down to give me a glucogenic precursor. Okay? Hello. Why you need to know all the details? Because there are so many diseases here, so many important biochemical reactions taking place. Okay, the most important thing about this degradation of methionine, and know if methionine is degraded, it can give rise to homocysteine. So one of the intermediate of methionine metabolism is homocysteine. Okay? Homocysteine is not a good molecule. Yes. Okay, what does it cause? An elevated homocysteine is the risk factor for what?
Anemia. بيعرف على اساس
Anemia? No. Something in the blood?
Sunflower in the blood. Beta thalassemia.
No, no. Yes, me? Yes. Yes, you Google it. And can cause actually atherosclerosis, okay? So it's very harmful to the blood vessels. There is a review article that a student wrote about homocysteine. I put the link for the review article. Inshallah, انتم تكتبوا review articles. He wrote it with Dr. Paul, one of Al-Faisal students. So homocysteine, you can write a review article about it. That's why you need to know this pathway very well. We will see in later slides that homocysteine concentration is related to the risk of having cardiovascular disease and death from cardiovascular disease. So the higher the homocysteine, then the higher the risk of dying from cardiovascular reactions. Yes?
How do you measure the levels of homocysteine?
You measure them in the blood. You measure them. Blood test. Okay. So methionine, to be broken down, the first step is to donate an adenosine to it. Okay. So it will take adenosine from which molecule? ATP. Okay. So we will take everything except the P, the 3P. Okay. So we'll take the sugar and the base, but not the phosphate, and we will add it to methionine. It will become SAM. Okay, who is SAM? As adenosine methionine. So it's methionine with adenosine. Where is the adenosine sitting? On the sulfur. That's why it's called SAM. Okay, remember, it has a sulfur group, methionine, right? So this SAM acts as a methyl group donor. What does the word mean, methyl group donor? It will donate methyl group. Who's going to take a methyl group? Yes, methyl acceptors like norepinephrine. Norepinephrine is a molecule that likes to be methylated, so they search for something like SAM to donate a methyl group for them. So once SAM has donated the methyl, it will become SAH. So it is now without the methyl group, and this molecule will be hydrolyzed to give me homocysteine. So we remove the adenosine, now we have homocysteine. Now we have exposed that sulfur group. Sulfur group inside methionine is not harmful, it's locked inside the molecule. Once it's exposed, this sulfhydryl group can easily react with other proteins or with other homocysteine and will make lots of oxidants. Yeah, it will become, it's an oxidant. Okay, so that's why it's not a nice molecule and it can injure the blood vessels. So the body must get rid of this homocysteine. How? Depend on the need of the cell and the availability of these cofactors. Okay, so homocysteine can be further broken down by cystathionin synthase. Okay, not broken down, it will be...
we add the serine.
Yes, we will add the serine and then we get cystathionin. Okay, so cystathionin is the homocysteine plus serine in it. Okay, this cystathionin is broken down by cystathionase and will give me cysteine and alpha-ketoglutarate. So the most important thing here to remember, in the homocysteine can be broken down to give me cysteine, and this is a very important enzyme, cystathionin synthase, and this is the cofactor which is B6, or it is derived from PLP, pyridoxamine. Or if the cell is deficient in methionine, then we can use this excess homocysteine to regenerate methionine directly, مش بس by going back. No, this is not reversible. So homocysteine will be acted upon by methionine synthase and will regenerate methionine. So we need a methyl group. Who's going to donate this time the methyl group? So it is N5-methyl tetrahydrofolate. Okay? It's different from the previous one that we saw in serine glycine. Okay? It's a different molecule, but it is a methyl donor. And it will become tetrahydrofolate. This molecule is derived from it's derived from what? From folic acid. Folate, so it's folic acid. So you need to have enough folic acid to go through this reaction. And also the coenzyme here is B12. So you need both B12 and folic acid. So to get rid of this homocysteine, you need to have folic acid, B12, and B6. That's why people who have elevated homocysteine in their blood, they are giving supplements with B6, B12, and folic acid, trying to lower. شو عم تعمل له؟ trying to lower the concentration of homocysteine. So supplementation with B6, B12, and folic acid is the way of lowering homocysteine in the blood. Okay, so this is what I have explained here. Next Thursday, inshallah, on Thursday we will continue with the synthesis. I put the attendance. We have another lecture.